Okay, for line segment rendering rasterization, as I said, the only thing remaining is to interpolate along the line, and we are going to also see things to make it more efficient. All right, so here's one thing that we can interpolate is color. For example, if this one endpoint is red, this endpoint is green. The line should, when we draw this line, there should be a smooth transition between this green to red to green. So we should see this smooth change. And how we can do that is by just interpolation. We could do bilinear interpolation by computing the distance, I mean, on the line itself. But there's a simpler way to do that. It's just an approximation, actually. It's not exact. We're going to do some interpolation, which will not be using the exact distance from these endpoints. We will be using the fact that our line is in the slope between 0 and 1. And when the line is between 0 and 1, its x-coordinate increases faster. So let's then just use the x-coordinate difference. For example, if this is the pixel that we are going to compute the color for, the distance that we will be looking for is x minus x0. And the total distance between the two endpoints of the line, we are going to treat them as if they're we're just going to use the projection of the line on the x-coordinate and do the interpolation on the projected distances. So x1 minus x0 is the projected distance of the line on the x-axis, the total line segment we are drawing, and the projected distance of this pixel, of this particular pixel, is x minus x0. So therefore, we are going to do a weighted average in which alpha is x minus x0 divided by x1 minus x0. How much, so it's just a ratio of where we are currently in the line. If we are exactly in the middle of the line, it will be, we will also be exactly in the middle of the line in terms of this x-coordinate. So it's actually a very good approximation. We will exactly get alpha is equal to 0.5. So as you can see, when alpha is small, it means that we are closer to x0, which means that we need to give a higher weight to the first color. So when alpha is closer to 0, so it's 1 minus alpha, just like we did in 1 minus t type of thing that it was an annotation that I drew, which is now erased, but I showed you this interpolation when Said asked this question about clipped lines have also their colors should be interpolated. We use t, the intersection point parameter t when we were doing that, and I said 1 minus t times the first point or the first color and t times the second color. It's exactly the same interpolation here. Okay, and this alpha variable can be computed by your x-coordinate like this. But we have some floating point operations here, but obviously you may not avoid floating point operations if whatever you're interpolating here it contains floating point values. For example, if this C here is not the integer color, you are bound to make, or I mean this ratio during this averaging, you may be forced to use floating point operations. So during interpolation, we may not ask for efficiency in terms of floating point operations, but we can still do one thing efficiently, which is making use of the coherence property again. For example, if I know that my color changes, for example, from red to green. What is red? 255, 0, 0. Green is 0, 255, 0, 0. In other words, from certain x0 to x1, my red channel is going to drop from 255 to 0. And this change is actually going to be constant. I mean, 2 pixels, we're always going to constantly subtract something from the red channel, and we're always going to add something to the green channel. And what we are adding is that how many pixels are you going to have along the line. So this interpolation parameter actually is 1 over x1 minus x0, right? Whatever the difference is, I mean, 255 was the difference in the red channel, right? From 255 minus 0, it's going to drop down to, or 0 minus 255, because it's a drop. We are going to decrement the color value. So it's going to be negative. 255 divided by x1 minus x0, that will be your unit increments at 1 pixel. So if you just, whatever your initial color value is, all you need to do is, this is your delta color in terms of the red channel. At every iteration, add this delta color to your color. I mean, if these are vectors, you can instead of treating them as scalar, you can do the same operation as if they are vectors. Okay, so what I'm saying is that the interpolating the color attribute constantly increases or constantly decreases along the line. So if we can compute this delta increase or delta decrease beforehand, instead of making the interpolation at every time step, we can convert this weighted averaging to just incremental updating of the color value. That's the efficient way to do that. And this is how the following slide actually implements that. Yeah, this is what it's all about. It says in the next, when x is 1 pixel to the right, the new alpha value is going to be this. Okay, it's just, this is the increment, and alpha 2 is going to be alpha 1 this. So every time the weight is increasing 1 over x1 minus x0. So if the weight is always increasing like this, we can find the color difference between 2 subsequent neighbor pixels. And this is exactly what this one does. So this DC is what I have written as delta C, the color increment. And they can, these C1, C0 values, they can be vectors, vector 3s, RGB values, which means that they are, the increment is a 3-dimensional value you have here, which is divided by a scalar. So this is my color, this is exactly what we did, right? 0 minus 255 divided by x1 minus 0, that's my constant color increase at every iteration. So this is going to be computed as a floating point value, but if your colors are integers like between 0 and 255, you again you may round it to the nearest integer before assigning it as a color to the pixel. So we just have this colored line, we have a new parameter to our draw function. It gets a pixel coordinate, integer pixel coordinate, and a color for that pixel coordinate, and that color is just every iteration, whatever we choose, left or right, it doesn't matter. I mean, left, east or northeast, it doesn't matter. At every iteration, the color is incremented by this delta color amount. This is how the interpolation is done. And instead of using color here, we could apply the same thing to the depth or to some normal vector along the line. So different interpolations for different parameters can be done by using this method. Okay, so this completes line drawing, line rasterization, and interpolating the color along the line. And for the second assignment, the things that you are going to be implementing, I mean, actually for line drawing code, is your pseudocode is exactly on this slide. So the slide 22 is the one you should use for implementing line drawing in the second assignment. But there are some things that you still need to do, right? I mean, like this is only for lines that are between slope 0 and 1. You need to take care of these edge cases, which may be cumbersome to code. But it's not so difficult. I mean, it's not that difficult anyways. You should be able to do this. It's just more lines of code than what it will appear here, but still doable. And this is the solution that you will be implementing for drawing lines. And the last thing we are going to talk about today is triangle rasterization. And I plan to finish it by the end of today's lecture. So that we will cover everything required for the second assignment, for the complete implementation of the second assignment. So here, for the triangle rasterization problem, we'll have instead of 2 endpoints, we'll have 3 endpoints, 3 vertices of the triangle, and our goal will be to draw all the pixels that are inside the triangle, on the edges and on the inside the triangle. There are different approaches. The one that we are going to describe here may not be the most efficient one. I think it can even be made more efficient. For example, what if we draw the lines first? Yeah, I think it will still require time. How do you determine pixels that are inside the triangle? For example, you don't want to miss, for example, what about if you draw a line here, can you immediately leave out, filter out other pixels that are above this edge equation? The algorithm we'll implement is going to be similar to this idea actually, but let's see. We're again using the implicit line equations. These are our edge equations. So the edge between vertex 0 and vertex 1, we call it F'01. So this is the line equation, implicit line equation for this edge. So for any pixel center, when we evaluate this line with it, if it turns out to be a positive number, it means that it's above the line and we don't draw this pixel. So all the pixels, I mean, what we are going to be doing is that these are our edge equations. We need to highlight pixels here in such a way that all of the pixels are below the lines. They all get negative values. For F'01, it should be negative. For F'20, so the way it's oriented is from 2 to 0. Below is this way. I mean, if you just think of it, you can also think about it like this. If this is the order of vertices in clockwise direction, it's just like being on the right of the line if you go on this direction. If you go on this direction, being on the right side of the line means you're going to get a negative value. Again, you're on the right side here, negative value. When you're going from 2 to 0, you're on the right side, you're going to get a negative value. So this is, but which pixels to test? That's another thing. Okay, if the pixel center is going to, for all these 3 line equations, if the pixel center gets negative values for all 3 of them, it means that the pixel is inside the triangle. Let's highlight those. But which pixels are we going to test? Are we going to test all of the pixels on my image? That's the least efficient you could do. What we will do is we will actually look at like a bounding box. So this is how the implementation is going to work. So the minimum x, minimum y, maximum x. So we are going to look at the rectangle rectangular area around the triangle, and all these pixel centers will be checked against those edge equations to see whether they are below or above. So for example, this pixel center is, since this pixel center is gives a positive value, it's not negative, so it's outside the triangle. And when we're drawing this triangle, these pixels are therefore going to be highlighted. Again, center is outside. When the pixel center is inside, we draw that triangle. So again, something that can be made efficient is that these line equations, we can make use of the coherence property as we rasterize this triangle on lines. For example, if this is the pixel center x0, xy, this is going to be x plus 1 y. So can we figure out its f value if we knew the f value of the previous one? So that by using that, we can make it more coherent. More efficient by using this coherence property. But in the implementation, in the second assignment, we are not going to ask you for this. We will not give a bonus to the fastest one or so. You're going to see that all of your implementations are going to be remarkably faster than ray tracing. So forward rendering pipeline, you're going to see it's much faster. You're not going to try to reduce from 10 minutes to seconds. I mean, it's already going to be seconds in all the scenes that you're rendering. It's going to render the entire scene very fast. So this projecting only the vertices first to this and running these rasterization algorithms is going to be much faster than ray tracing. So yeah, the algorithm for we are going to walk along the pixels within the bounding box. For each pixel we make this inside test with respect to all three edges. We plug in the XY pixel center value. If they're all negative, then the pixel is inside the triangle, as I said before. And also, what about the interpolation of the attributes? When we have this pixel center, how are we going to interpolate the color values at the vertices for this pixel, for example, for this XY? We can now, for that one, we can actually revert to the barycentric coordinates. We have to use the barycentric coordinates for interpolation. If you remember, barycentric coordinates was defined in such a way that it's like the ratio that is assigned to this x0, y0, or the weight that is assigned to this is the ratio of this area A0 to the entire triangle area. And since this is in all of the denominators are A here, we don't need to actually compute them, but A0, A1, and A2, we need to compute these. And this value can be found by, again, looking at how far this point is from the line. Okay, for example, when A0 is going to be largest, when this yellow point is exactly on this vertex. It will happen when this A0 is as far away as from this edge. And implicit line equations are going to help us in that regard. So we will be using implicit line equations to compute alpha, beta, gamma. You don't need to memorize these, but just know after you have an implicit line equation implemented, you're going to have the edge equation. So F'22 is this one. So here we have to refer to this one. If you look at the F'12's function, it gets the vertices 1 and 2 as the constants, and xy is the parameter that we plug into this line function. So if you plug in to your edge function your pixels coordinates, and if you also evaluate it at x0, y0, okay, so x0, y0 is the farthest it can be, right? I mean, this is the F'12, so f0, y0 is the farthest it's going to be. So if they happen to be if your pixel happens to be as far as this part, it's going to be exactly equal to F'12, and alpha is going to be equal to 1. And as this one is going this way, F'12 is going to be smaller than, I mean, since this is the farthest it can go, so this is the largest value it can have. So we are basically, let me use the annotation, we are basically using the ratio of these two things, okay? So this implicit line equation gives us some negative positive values, but here for triangle rasterization interpolation of attributes, we make use of also the magnitude of these implicit line equations. The magnitude is proportional to the distance of the point from the line. Therefore, we are going to use since if you look at these areas, for example, the area is going to be, the base is the same. The area is proportional to height of this, the distance of this point to this line. So the alpha value, the barycentric coordinates, can actually be found by directly these ratios, by looking at the ratio of plugging in your pixels coordinate to these. The denominators are all constants here, as you can see, for each edge, which defines a particular alpha, beta, gamma. By the way, I mean, if you know alpha and beta, you don't need to compute gamma like this, because they need to, oh, do they need to add up to 1? No, because we will be computing this alpha, beta, gamma also for pixels that may be potentially outside the triangle. Okay, we will be using actually alpha, beta, gamma for inclusion test as well, because for a triangle that is, for a pixel that is inside the triangle, uh, all of alpha, beta, and gamma, they should be positive. Okay, if all of them are positive, it means the pixel is inside the triangle. So since we are going to be computing alpha, beta, gamma for interpolation anyways, we can also use them for inclusion tests, whether to understand whether a pixel is inside or outside. So here's the overall triangle rasterization algorithm. This is the part where we test all of the pixels in the bounding box. So we have two while loops, two for loops, y coordinate from y min to y max and x min to x max, and we compute alpha, beta, and gamma like this. Gamma, we don't say gamma is equal to 1 minus alpha minus beta. This is critical, okay? Because we compute alpha, beta, gamma for a pixel that is potentially outside the triangle too. Okay, so therefore, when one of them may be negative, for example, when we do that. If all of them are positive, then the triangle should be, if all of them are positive, means that we know that, for example, for F'12, for example, going this way, x0, y0 is to the right. So this, we know that the denominators are all negative. Okay, so this is a negative value. This is a negative value. Negative value. In order for when we were testing a pixel to be inside, remember we wanted these numerators all to be negative with respect to each of these edges. This is the same test. I mean, if the denominators are all negative, checking whether alpha, beta, and gamma are all positive is the same test as we have this situation here. We plug in the xy value of the visited pixel to each line equation. If all are negative, the pixel is inside the triangle. The same test we do here, we are again checking whether all of these numerators are negative. But since the denominators are also negative too, these are on the same side as this edge for a pixel that is inside, therefore they're also, all of them are negative, but with larger values negative. For a pixel to be inside, all alpha, beta, gamma needs to be positive. So this is, therefore, if you're confused about this equation, oh, we wanted them to be negative, why we are asking them to be positive? Because we just computed the barycentric coordinates with this division, and they need to be all positive in order for the pixel to be inside. If that's the case, then we just compute the color value as an interpolation of alpha, beta, gamma like this, and we just draw the pixel at that coordinate with this color. And again, the computation of the barycentric coordinates, for example, may be made incremental for greater efficiency. What I mean is that when x is incremented one by one, how alpha, beta, and gamma, how your barycentric coordinates change. What is the increment in your barycentric coordinates as you move along the scan line, along the horizontal line? If you know that, instead of computing them from scratch every time, you can just add those increments. And when you move, for example, to the next horizontal line, what should you update? So you need to think about two things. While you're on the same horizontal line, how your alpha, beta, gamma values change. And when you get to the next horizontal line, if when you increment y, or when you get to the next horizontal line, which may be above, how again your initial value at the beginning of this horizontal line changes. You need to think about these things, but you don't need to, for the assignment, you don't need to implement this more efficient one. Okay, implementing this original one that is represented on this slide will be sufficient. Okay, we don't want but if you want a faster algorithm, you may do that. It will be very difficult to do. One thing that you can do efficiently is, if you see the denominators here, they're all constants. You should just compute them outside the for loops and just divide every time x and y changes, divide them by these constants. Okay, so this one, I think this is an image, that's why I cannot select this one. Let me see. Yeah, it's an image. Yeah, I can actually, inside the image I can select. So let me quickly get rid of these. So just to show you, yeah, these parts that I've highlighted, the denominators, they're constants, as you can see, which doesn't depend on the loop variables. So you can compute them outside the loop and divide them then within the loop. So you can do it for more efficiency. And that's it. At this point, what we know is how to draw triangles on the pixels and draw also line segments on the pixels and interpolate attributes that are assigned to their endpoints. So the result at this point is are fragments of triangles, are fragments of line segments. And on Thursday, we are going to talk about, at this point, your assignment 2 just covers everything up to this point. But we are going to see things like how do we run this depth buffer algorithm so that objects that are behind do not get to update the pixels. How we can maybe use texture mapping on this. Each fragment here has different attribute values of attributes, and they are processed further to determine. I mean, the main processing that we will see is the depth buffering, but there are other tests too. For example, there is something called stencil buffering, which we will see in shadow volumes. There's an algorithm for creating shadows. Shadow mapping algorithm uses depth buffer too, but there's shadow volumes algorithm which uses a different buffer called stencil buffer, or sometimes called accumulation buffer, which can be used to count things. For example, how many pixels are past this test? You can put a binary Boolean test for each pixel, and you can use that buffer as a counter to see how many pixels have passed this test or not. So there are different things you can do with fragments. You can do for different effects like fogs or depth of field blurring. That's something. Actually, some of the shows, TV shows, actually use this depth of field blurring. Sometimes, if you notice this, it may get really annoying, which means that, I mean, you want the entire image to be sharp, right? But in real world, I think wherever we focus on is sharper than the boundaries. I mean, just think about your peripheral vision. It's not as sharp as where you're looking. In order to simulate this on the generated images in games, for example, the part that you focus on as sharp as possible, but the outside places are blurred to simulate this real life vision. But if you're watching a TV show, for example, you want I don't know how they're going to know where you're looking at, but I mean, I think they want to focus on certain regions at every time. One of the TV shows, what was the name? There are a couple of TV shows that uses this, but they did this particular, specific blurring of parts of the video, like the edges. The edges appear blurry, but the center is really sharp. There was this Homecoming. Yeah, Homecoming is that one of the TV show. that uses this idea. It was really apparent. It was really annoying. For example, when you look at the table's edges, they were really blurry. But if you look at the center, it's not so blurry. You can do these effects, for example. This is called depth of field blurring. You can apply these, for example, at the fragment processing stage. When you have the fragments, you can apply additional effects to them. And this is some of these we are going to start talking about them on Thursday. And in the final 4 weeks, we are going to start learning about how we can tap into hardware acceleration and write code for the GPU, how we can send our vertices, our transformations to the GPU so that the GPU renders them automatically for us. All these interpolation, rasterization will be done automatically by the GPU, and we are going to see how we can do that. I'm going to show you some example programs as well. Okay, so we actually have finished a little bit early today, so I'm not going to start on the next topic, which is that fragment processing. But if you have any questions, I'll be happy to answer them. Otherwise, I will continue with fragment processing on Thursday. And if you have any questions about the assignment, feel free to ask your questions to us, to the assistants, okay? And have a nice week, everyone. That's it from me today. I will stop recording now.